So we saw that spanning a subspace with linearly independent vectors is the best way to do it because, first of all, it gives you unique representations, unique linear combinations, and also adding or removing any vectors from this list and keeping this list linearly independent would change the vector space. So spanning with linearly independent vectors really is the best way to span a vector space. And so if we have a collection of vectors, linearly independent vectors that spans a subspace, we'll give that collection a special name. So we'll call it a basis. So a basis for a subspace. So if you have a subspace, a basis for that subspace is a list of vectors, which for us will always be finite, a list of vectors that spans the subspace and is also linearly independent. So this collection of vectors is not only does it span the space, but it spans it in the most efficient way possible. Because these vectors are all linearly independent, if you removed one of these vectors from this spanning subset, it would no longer span the same space. So let's look at some examples of a basis. I guess one important thing to notice is so spanning these in this list of vectors, because they're linearly independent, these in this list, you can't throw away any vectors, but it's entirely possible that a different list of vectors could span the same space, right? So it doesn't have to be these vectors exactly. So if you start with these vectors, you can't remove any of them, but it's possible that there's a completely different list of vectors that does span the same space and is still linearly independent. I guess let me write an example of that. So let's take R2 for an example. So R2, all of R2 is the span of 1, 0, and 0, 1. So these are clearly linearly independent, right? When you have two vectors in a set, they're linearly independent if they aren't scalar multiples of each other, and these two are definitely not scalar multiples of each other. Also, they clearly span R2 because everything in R2 is a linear combination of these two. Okay, but let's consider, so that means that this collection of vectors, 1, 0, and 0, 1, is a basis for R2. Okay, well let's consider a different collection of vectors. How about 1, 1, and 0, 1? So, I'm sorry, not 1, 1, and 0, 1. That example would work, but it's not the one that I meant to write down. 1, 1, and 1 minus 1. Okay, so on the one hand, these are linearly independent, so I'll let you work it out, but if you row reduce the matrix 1, 1, 1 minus 1, it row reduces to the identity matrix, and so that means that the only linear combination of these vectors that adds up to 0 is the trivial linear combination. So these are linearly independent. So now the question is, does it span all of R2? Well, on the one hand, the vector 1, 0 is a linear combination of these two, because it's 1/2, 1, 1, plus 1/2, 1 minus 1. So right, 1, 0 is in this span of these two vectors. Also, 0, 1 is in the span of these two vectors because it's minus 1/2, 1, 0, plus 1/2, 0, 1. So 0, 1 and 1, 0 are both in this second span, but that means every linear combination of 1, 0, and 0, 1 is also in this span, but 1, 1 and 1 minus 1 is in the span of 1, 0, and 0, 1. So these two spans are equal. So in particular, the second one is also equal to R2. So you can see that these spanning sets are different, right? But they do span the same space. So we have to be a little careful with span still. All right, so let's look at some other examples of bases for subspaces. So let's look at this subspace. So A, B, the all collection of vectors A, B, 0, where A and B are scalars. And let's ask which of these collections is a basis. So one way to try to figure that out is write this, try to find a set of vectors in here that spans this set. Well, like we did with the previous example, we could write this, right, this vector a, b, 0 as a times 1, 0, 0 plus b times 0, 1, 0. Right? And a and b are scalars. Okay, so this subspace V, it's a span of these two vectors. Well, that's these two vectors. So these two vectors span our subspace V. So is it a basis? Well, to check if it's a basis, we have to know that it spans, but we also have to know that it's linearly independent. So are these vectors linearly independent? Well, clearly yes, because if you stuff them into a matrix and row reduce, do you have a pivot in every column? Well, it is already row reduced, so we don't have any work to do to row reduce, and there is a pivot in every column. So these vectors are linearly independent. So this is a basis. Okay, now let's look at this one. So clearly, because this second collection contains 1, 0, 0 and 0, 1, 0 and some other stuff, it definitely contains V. 1, 1, 0 was in V to begin with, so we don't accidentally get anything more than V. So these three vectors span V, but are they linearly independent? Well, clearly not, because this last vector is the sum of the first two. So there is a linear dependence between these. So although these do span V, they're not linearly independent. So these three vectors do not form a basis. So not a basis for V. All right, what about this collection of vectors? Clearly linearly independent. If you have a single non-zero vector, it's always linearly independent. But does it span V? Well, clearly not. I mean, the span of this vector is all vectors that look like A, 0, 0, but we can never get that second entry to be non-zero. So this doesn't span V. Because it doesn't span enough, right? So this is not a basis for V. Okay, final example here. Does this span V? Well, these are definitely linearly independent vectors, but what are the span of these? The span here is clearly all of R3, right? These are the elementary unit vectors for R3. So these span all of R3, right? If you chose constants or scalar multiples A, B, and C and multiplied and added up, you'd get the vector A, B, C. But this could be anything in all of R3. So these three vectors span all of R3. So they are linearly independent, but they span too much. So still they're not a basis for V, because they don't span V, they span too much. All right, so you can see being a basis is actually a pretty stringent requirement. You have to be linearly independent, and you have to span exactly the space that you're looking for. Notice, though, that even though it could be tricky to come up with a basis, we know that every subspace has a basis, because one of the things that we proved earlier is that it's possible to write V as a span of some vectors, and it's possible to arrange things so that these vectors are linearly independent. But these are exactly the requirements we need for this collection to be a basis. So that theorem that we proved really demonstrates that every subspace has a basis. Right? It might be difficult to come up with it, but there definitely is a basis. In fact, there are lots of different ways to choose a basis for a vector space. If you go back and look at the proof of this fact, the way we proved it was just by making a lot of choices for vectors, right? We started with one of these vectors, and then we chose vectors outside of the span of what we've already chosen. And every time, every step in that process, there are lots of different ways to choose a new vector. And so every different choice of a new vector gives you a different basis. So there are lots of different bases to choose, but there definitely is at least one.